Hey everyone, today I want to show you how to find the general term of a geometric sequence given its ratio. So essentially any term of a geometric sequence if you know the common ratio. So we have the sequence here 4, 16, 64. The first thing we want to establish is what the common ratio actually is. So we can do that. To do that you just need the second term divided by the first term. So we have 16 over 4 is equal to 4. So our common ratio here is 4. Now we want to plug it into the general term equation here, which is a1, or a times r to the power of k minus 1, where k is the term you're actually looking for, r is your ratio, and a is the first term of the sequence. So let's say we're looking for the fifth term here of this particular sequence. We know the ratio, that's 4, and we know the first term, that's also 4, so we can do 4 times 4 to the power of, since we're looking for the fifth term, we'll do it to the power of 5 minus 1. That's a really bad 5. Power of 5 minus 1. And this right here should give you your equation. So, looking at this, we have 5 minus 1, which is 4. So 4 to the 4th, well 4 to the 3rd is what, 64? 64 times 4 is what, 256? Yeah. So 256 times 4, we'll do that up here. 256 times 4, that gets you 1024. So we have that, the fifth sequence in this number, the fifth number in the sequence is 1024. So we'll say that when k equals 5, as in when we're looking for the fifth term, that yields 1024 here. So 1024 is the fifth term of the sequence. And that's how you would find it with the equation a times r to the power of k minus 1. So now that we know that, I want to pose sort of a reverse question. There you go. So what I mean by reverse question is, let's say you know that a1, so the first term in the sequence, is 3. You also know that a3, third term in the sequence, is 27. We want to find ak, so whatever term this is, the kth term, and that equals 4,782,969. And we're looking for k, so we'll say find k. So this type of question is a little harder, because now usually to find the ratio you look at two consecutive terms. You divide two consecutive terms. But in this case, we don't have two consecutive terms. We have the first term and the third term, so we can't just divide 27 by 3 and expect that to be our ratio. Not only that, it's not that we know what term we're looking for and we're trying to see what term or what number corresponds to that term. Rather, we know the number, but we don't know which term. We're trying to find which position in the index is this number at. So in this case, 4,782,969 is a pretty large number, so we know it's going to be a little later in the sequence. But the first thing I want to establish is the actual common ratio. So while we cannot simply divide and have that be our common ratio, we do know that in a geometric sequence, since we're multiplying, to essentially skip terms, we want to raise the ratio to a power. So if I had, for instance, 1, and then 3, and then 9, and 27, to get from 1 to 27, right, we're skipping terms, so I have to raise 3 to a power. So to do the inverse of that, to essentially remove that raising to a power, we want to square root something. So we'll do 27 over 3. And that gets us 9. But now, since we're skipping terms, we only skip the second term. So we're essentially, instead of raising 9 to a power, we want to sort of, I guess, decrease it. So we want to find the square root of 9, because we're only skipping one term. So we do square root of 9, it's just 3. So we know that the ratio now is 3, and of course we can check that. 3 times 3 is 9, 9 times 3 is 27, and that would correspond to the third term, so the ratio is in fact 3. Next, though, now we know our ratio, and we know our first term. We can plug that into the equation I had earlier, so we have 3 times 3, our ratio, raised to the power of k minus 1. But this time, instead of plugging in k and seeing what that actually gets us, we know what it will get us, which is 4,782,000. That's a really bad 8. 782,969. We know that it will get us this. Now we're looking for what k actually is. So this is a simple equation we can solve out. So we do divide by 3 on both sides. That cancels out over 3. We'll write our new equation over here. And that'll be 3 to the k minus 1 equals, and then 4,782,969 divided by 3 is 1,594,323. So now, essentially what we want is we want to find k. And in order to do this is kind of like a reverse exponent. And, well, a reverse exponent in math is a logarithm. So what we're really looking for is log base 3 of 1,594,323 equals something. So let me just do that. I'll type the whole thing out. Okay. Okay. That's not what I want. Why isn't there a calculator for this? Here, I'll do that. That is not right. Hold on. Okay, there you go, 13. Alright, so log base 3 of 1,594,323 is 13. However, we're not done just yet. If we plug k in for 13, we get 13 minus 1. That's 12. 3 to the 12th is not 1 million. 1.5 million. Instead, 3 to the 12th is actually 531,441. So not only did we not get 1.5 million, we certainly didn't get 4.7 million, which is what we're actually looking for. So what we do from here is, we know k equals 13. And since 13, 3 to 13th, we'll just do that out right here. 3 to 13th, that's 3 to 3rd. So we see it's 1.5 million. But in order to essentially reverse the effects of this, since we're not looking for this, we're looking for the numbers after this, we want to add 1 to 13. So we'll do 13 plus 1, which is 14. And now that we have the 14, we can check that. 3 to the 14 is in fact 4.782 million, 4,782,969. So we can safely say now that k equals 14. So that's both how to find the general term of a geometric sequence, and also sort of a reverse question where you don't know the term, you just know the number, you're looking for what term that number corresponds to. So yeah, thank you for watching.